Hello, welcome to Meki Teki. Learn as engineer, teach as champion. First of all, I would like to thank my family for their continuous support and encouragement of creating these kinds of technical videos in public domain. And I would like to thank my mentor, Professor R. Surendran from Government College of Technology, Coimbatore, for igniting me a spark of creating these kinds of technical videos in public domain. And I would like to thank Almighty, my God, for my good health and broad mind, and my dear friends, followers, my dear students and subscribers for their continuous support. Today's topic of interest is thermodynamic processes. We know that the thermodynamic system consists of the several processes. These processes are categorized as per whether it is an open system or a closed system. In closed system, with the help of the different assumptions, we are formulating different kinds of a process, so that we are going to discuss over here. Here, very important point is we are going to do a PV diagram and TS diagram. I'm saying PV and TS, that is pressure, volume, temperature, entropy. So these four we are going to take a consideration, and we put a plot for different processes, and we'll get the exact value of the process. Here, first we are going to discuss about work. So work is the outcome of PV diagram. The area below the PV diagram, that is area below PV diagram, which is called work. Area below the PV diagram, which is called as an work for the closed system. So first we are going to discuss about the closed and the open system. First, let me go into my own content, that is work. For non-flow work, when I am saying non-flow work, it is for the closed system work, which is boundary work. The work can cross the boundary where the mass and heat remains in the boundary. So the condition is the system is closed, quasi-static, that is the process is reversible. Work should cross the boundary and remaining things won't cross the boundary. For the reversible, external pressure is equal to internal pressure. We know that the external pressure is equal to internal pressure, and work is the area under PV diagram represents work interaction for a closed system. That is, difference in work is equal to pressure into difference in volume. So this is the difference in volume means change in volume. So this is the formula for finding work done in the closed system. So directly I go to the work for the flow and non-flow process and the outcome. We are going in this process, we are going to find the work and outcomes and the different kinds of a process. These processes are derived from the perfect gas law, that is PV by T is equal to constant. This constant is nothing but m into R, mass times of R. So here this component is very important. When I am saying a volume is equal to constant in PV by T, here the volume is equal to constant for the process 1 and 2. As I said, P1 by T1 is equal to P2 by T2. Similarly, for pressure is equal to constant, we put the pressure is equal to constant, and similarly if the T is equal to constant, so this T will become constant. For P is equal to constant, it is V1 by T1 is equal to V2 by T2, where T is equal to constant, it is P1 V1 is equal to P2 V2. Similarly, For the adiabatic and polytropic process, we use a gas constant law. PV power n is equal to constant. If n is equal to gamma, it is adiabatic. If n is equal to n, then it is called polytropic process. These different forms of the n, I'm going to clearly about, I will give very clearly about this n, how the n is differ. So this thing I am going to make it clear. If all the formulas can be formulated from this formula, PV power n is equal to constant. If this n is equal to infinity, that is equal to constant volume process, therefore volume is equal to constant. If n is equal to 0, then this process is called constant pressure process. If n is equal to 1, it is called temperature constant process. If n is equal to gamma, it is an adiabatic. If n is equal to n, then it is polytropic process. So this is how, from this equation also, the different kinds of the process can be categorized. In such conditions, first we are going to discuss about the work for the non-flow and the flow process. The outcomes are, we are going to discuss. Here we are going to see that is PV power n by T. That is the formula. Okay. So here I am saying that for constant volume process, the volume is equal to constant. Therefore, in non-flow process deals with P into dV, and flow process deals with V into dP. Therefore, in non-flow process, the work done for constant volume process is 0. And if you see the gas equation, that is uh, Q is equal to del U plus W. This is the first outcome of the first law. So if W is equal to 0 and Q is equal to del U, so this is the heat, this is the outcome of the constant volume process. In constant volume process, heat is equal to internal energy. So the net heat input will becomes net internal energy. So here n is equal to infinity. So this is how you have to categorize. So this is P into dV and this is V into dP. Okay. Next is a constant pressure process. Here the pressure is equal to constant. Therefore W is equal to P into V2 minus V1. Therefore the flow process, the work done is equal to 0, and hence the Q, which is equal to del H. Q is equal to del H. What is meant by H? It is an enthalpy. Enthalpy is equal to P into dV. So enthalpy is equal to P into dV. Therefore, Q is equal to del U plus W, that is P into dV. Here del U is equal to 0, where Q is equal to P dV. That is a change in enthalpy. And similarly, for the constant temperature process, for the flow process and non-flow process, both are same, that is PdV and VdP, both are same. Therefore W is equal to P1 V1 ln of V2 by V1, and W is equal to P1 V1 ln of V2 by V1. Here Q is equal to W. So Q is equal to W. This constant temperature process is the definition of the Joule's experiment, that is first law of thermodynamics. The first law of thermodynamics deals with when it satisfies, if we are become the heat is equal to constant at constant temperature, the net heat input is equal to net work output, then the first law of thermodynamics becomes equal. So this is what the perpetual motion machine 1 says. Perpetual motion machine 1 says. Okay. And next is an adiabatic process. That is, in adiabatic process, entropy is equal to constant. Entropy is equal to constant. PV power n is equal to constant, where it is a non-flow process P into dV and a flow process V into dP. Here the as per this equation, the work done P1 V1 minus P2 V2 the whole divided by gamma minus 1, whereas the W for the flow process gamma into P1 V1 minus P2 V2 whole divided by gamma minus 1. Here in adiabatic process, net heat is equal to 0, therefore work done is equal to minus of internal energy. Work done is equal to minus of internal energy. Here the work done is equal to internal energy, we can say work done is equal to internal energy. And for the polytropic process PV power n is equal to constant, where work done, if it is a non-flow process, the work done for the adiabatic and polytropic process are similar, whereas here it is gamma, here it is n. That is how. And similarly for for flow process also, instead of gamma, if we put n, it is very similar for the work done for the polytropic and adiabatic process. Whereas heat, the heat generated is equal to gamma minus n divided by gamma minus 1 into W, since n is equal to n. And for your information, for all process change in internal energy, that is du is equal to m into specific heat at constant volume into change in temperature. And for all process, the enthalpy is equal to mcp into del T. Here the specific heat at constant pressure is, if there is a constant pressure, it have a term of enthalpy. If it is a constant volume, it is called internal energy. If I put this capital U into small u, then it is called a specific internal energy. The specific internal energy, which the mass is a inbuilt quantity. The specific internal energy, so del U is equal to CV into dt, and specific enthalpy, so specific enthalpy dH is equal to Cp into dt. So if I say it's specific, it is an intensive property, whereas this is an extensive property. So you can clearly notice this. So this is an extensive, so this is an intensive property. Okay. And for air, the gamma value is 1.4, and R, universal gas constant R is equal to 0.287 kilojoule per kg Kelvin, and Cp, specific heat at constant pressure, is equal to 1.005 kilojoule per kg Kelvin, and Cv is equal to 0.718 kilojoule per kg Kelvin. Here with this you have a notice this, when I say gamma, this is Cp by Cv, and when I say R, this is Cp minus Cv. So this is the relationship between the air constant and the universal gas constant. So this you have to notice. And now we are going to discuss about the process and conditions and their PV and TS diagrams. First, it is a constant volume process. A constant volume or an isochoric process. It is functioning on Gay-Lussac law, where P2 by P1 is equal to T2 by T1. Since the volume is constant, the TS diagram will have a steep curve. The volume is constant, it is a steep curve. And similarly, if the pressure is constant, in PV diagram we have a horizontal line. Here you have to notice this. If the vertical line, in the sense, the vertical line here, n is equal to infinity, and for the horizontal line n is equal to 0. N is equal to 0. The constant pressure process or isobaric process, it is working on Charles law, that is V2 by V1 is equal to T2 by T1. Whereas you compare in TS diagram, if we say a steep curve, that is volume is equal to constant, if there is a a little bit a flat curve, it is called pressure is equal to constant. The pressure is equal to constant. You can notice this, the different graph of TS diagrams. And similarly, for the isothermal process, it is a constant temperature process. It is working on Boyle's law, where T is equal to constant, P2 by P1 is equal to V1 by V2. So this isothermal process will violate the first law of thermodynamics. Will violates first law of thermodynamics. So this curve, the PV curve here, the n is equal to 1. The n is equal to 1. The PV curve is a hyperbolic curve. In isothermal process, the PV curve is an hyperbolic curve. Therefore, the slope m is equal to pressure by volume. And TS diagram, since it is a constant temperature cycle, it is a constant temperature process. Therefore, temperature is equal to constant, where S is differ. Yes, will get differ. And for the adiabatic process, no heat transfer occurs. In adiabatic process, there is no heat transfer occurs. In isentropic process, then there is no friction and no heat transfer. The isentropic process are reversible adiabatic process. This thing you have to notice this. In many of the books, they say adiabatic and isentropic process are same, but in nature it is different. If I say adiabatic process, we are not at all considering a friction as a term, whereas no heat transfer is occurs. And it is an isentropic process, there is no friction and no heat transfer. The isentropic process is also called as reversible adiabatic process. Here the PV power gamma is equal to constant. And similarly, the relationship between the PVT have been given here. We have to notice this. See, here the S is equal to constant. Then the TS diagram, S is equal to constant. Whereas in constant temperature process, the T is equal to constant. Where in adiabatic process, S is equal to constant. So we have to compare the PV diagrams. So if there is a steeper curve, that is called isentropic process. If it is very a flat curve compared to the adiabatic, which is called temperature is equal to constant. So when T is equal to constant, it is called as hyperbolic process. When T is equal to constant, it is called a hyperbolic process. A hyperbolic curve is there. Next is a polytropic process. PV power n is equal to constant. In this polytropic process, there is no definite PV and TS diagram. According to the n conditions, according to the condition of n, we have put n processes. When it is a 0 to 1, the process is like this. When it is 1 to 1.4, this is like this. 1.4 to infinity, 1.4 to infinity is this. 1 to 1.4 is this. So like this, the PV diagram and TS diagram, which is having a 3 more curves. So according to the polytropic index, the PV and TS diagram is being varied. So here next I'm going to discuss about, we're going to compare all the PV diagram and TS diagram in one PV diagram. So if I said I'm having a constant volume process, my constant volume process PV diagram is this, and TS diagram will have a steep curve. If I said constant pressure process, my PV diagram is like horizontal line, whereas in TS diagram it is bit a flatter line, then volume is equal to constant. When I said it is a constant temperature process, my PV diagram is like this, a hyperbolic curve, where in TS diagram it is horizontal. If I said adiabatic process, in TS diagram we have a constant enthalpy curve, and here it is this. And for the polytropic, it is intermittent of constant pressure and isentropic and isothermal. So and volume, constant volume process. So it is an intermittent process of these four processes. So you can see in PV and TS diagram, it is intermittent of this thing. Okay, I hope you have get a better clarity about this PV and TS diagram within a single curve. So this is my idea to know the terms within a single graph. So this is the CP and CV curve for the monoatomic and non-monoatomic gases. Here I would like to plot a graph of the specific heats and temperature. According to the temperature, if it is a non-monoatomic, it is a increasing process. When it is a monoatomic, the CP and CV are constant for that temperature. For the different temperature, if I increase the temperature for the non-monoatomic gases, the value of Cp is increased, Cv is increased. We know that gamma is equal to Cp by Cv. When this is also increased, but this will get decreased. If it is a monoatomic gas, all are constant. So with this, I am going to complete the process. Next, the first law of thermodynamics, that is the outcome of the Joule's experiment, we are going to discuss. The first law of thermodynamics deals with the conservation of energy for a closed cycle. Cyclic integral of heat, change in heat is equal to cyclic integral of change in W. Therefore, it is not at all possible to convert all the heat into work. That is why the internal energy, the difference in energy, will come into picture. So, delta Q is equal to difference in energy plus the change in work. Here, the first law of thermodynamics is valid only for the closed system and undergoing a process as well as cycle. Both are reversible and irreversible cases. This formula will get valid. And similarly, and we are going to introduce a different kinds of formulas and conditions how the first law of thermodynamics is varied. If I said it is a closed system and a quasi-static process, that is reversible process, then del W is equal to P dV. And if I say adiabatic, reversible and ideal gas, then PV power gamma is equal to constant. So this relation come into picture. If I say it is a closed system, del Q is equal to del E into del W, and a closed system having kinetic energy is there, and whereas potential energy is zero. That is why the change in energy, that is internal energy, coming to picture. If there is kinetic energy is zero, potential energy is there, the quasi-static process of closed system, instead of del W we put PdV. So instead of del W we put a PdV. If we know this first law of thermodynamics definition and this difference, we have to know that the consequences of first law of thermodynamics. What is the consequences? Heat transfer is a path function. And change in energy, difference in energy, is an internal energy. So internal energy is the property which is the outcome of the first law of thermodynamics. The first law of thermodynamics gives the internal energy, that is change in energy. And the energy of an isolated system is always constant. That is why we are not at all using an isolated system at any process or the first law of thermodynamics. The energy is a point function and extensive property, whereas specific energy is an intensive property. Okay, so this consequences leads to perpetual motion machine, The perpetual motion machine, what it gives, ppm1, it is impossible that a machine working without input energy. So without input energy, any machine won't work. So that you have to know that. So when we convert Q is equal to W, so there is the input is equal to W, the Q is equal to W. So next is a pressure. We know that the value of pressure for normal air, and I'm going to give the pressure is not an energy. It only tells the energy per unit volume, that is energy concentration. This you have to notice this. The relationship between the pressure and energy. We know that pressure is not an energy, but it only tells the energy per unit volume. We know that work ratio is equal to 1 minus Cp by Cv, that is work ratio Wr is equal to 1 minus 1 divided by gamma. This gamma for monoatomic gases, the monoatomic gases are having maximum amount of gamma, that is 1.67. For diatomic gases it is 1.4, and polyatomic gases the gamma value is 1.3. When I say polytropic index, N is equal to 1.3, it indicates polyatomic gas. When I say adiabatic process, the adiabatic index gamma is equal to 1.4, it is a diatomic gases. So this also you have to understand, and you have to add these points in the polytropic and adiabatic process. Next, the enthalpy. Enthalpy H is equal to internal energy plus PdV, and entropy is derived from TS diagram. ds is equal to T into dt, that is degree of disorderness or degree of randomness. And Mayer equation gives Cp minus Cv is equal to R, where Cv is equal to R divided by gamma minus 1, where Cp is equal to gamma R divided by gamma minus 1. So with this, I'm going to conclude today's session about the thermodynamic processes. I hope you have understood better in thermodynamic processes. And if you have any doubts, please let me know in the comment section, and I will put definitely another video for clarifying your doubts. So until then, bye bye from Santhosh. Thank you for patient listening.